Okay, welcome everyone. It's my great pleasure to have Z Huang visit us. Z is no stranger to these parts, having interned here multiple times and visited here multiple times. But it's always great to have him back. He's now a professor at the University of Hong Kong. And he's going to tell us about fully online matching, some recent very exciting work on online matching. So over to Z.
Okay. Thanks, Nikhil, and thanks for having me here, and thank you all for coming. So today I'm going to talk about fully online matching, a new online matching model that generalizes the classic online bipartite matching, which we all know and love, and it's motivated by some modern applications such as a ride-sharing platform. Okay, so it's a joint work with a bunch of students in Hong Kong U, Ning Kang, Zhihao Tang, Xiaowei Wu, Yuhao Zhang, and Xue Zhu. So to start with, let's give a very quick recap of the classic online bipartite matching problem. So in this case, we have a bipartite graph. One side of the vertices, let's say the left-hand side, are known as offline vertices. They are given to the algorithm upfront. The other side, on the other hand, arrive one by one. On the arrival of an online vertex, its incident edges will be revealed to the algorithm, and at this point, the algorithm must immediately decide what to do with this vertex. We can check whether any of its neighbors is still available. If so, which neighbor do we match it to? Okay. So for example, suppose we match it to the second neighbor, the second vertex come, two neighbors, again match to the second one, and so on and so forth. At some point, it might be the case that some vertex arrive, but all its neighbors are already matched. Since this is an online model, we cannot revoke our previous decision, then there's nothing we can do. We can just simply leave it unmatched. Same apply to the fifth online vertex. Now in this case, the algorithm managed to match 3 pairs, so we say that its performance is 3, while in hindsight, we can easily figure out that there's actually a way to find a perfect matching, so the optimal get 5 pairs. So the ratio, 0.6, will be the comparative ratio of the algorithm for this particular instance. So what I showed in the last slides is basically a very naive, greedy algorithm that tried to match each online vertex to an arbitrary unmatched neighbor, if there exists any. And it's very easy to show that this is 1/2 competitive, and this is the best ratio for a naive, greedy algorithm. So given that such a simple algorithm gives you 0.5, the natural thing to ask is that can we beat 0.5, and what's the best number? So this is basically settled almost 3 decades ago by this seminal work by Karp Vazirani in Stock 1990. They proposed the ranking algorithm, which has the following very simple but cool idea of picking a uniformly at random permutation over the offline vertices at the very beginning and keep the same permutation over time. So on the arrival of each online vertex, it simply look at all its available neighbors and pick the one that has the smallest rank. Okay, in this case, the first neighbor has rank 3, which is the smallest, so match it to the first neighbor. Second vertex come, 2 is smaller than 5, match it to this guy with rank 2, and so on and so forth. So it turns out that for this particular realization of the ranking algorithm actually managed to match 4 edges. And of course, we will measure such randomized algorithm based on the expected number of edges that they get over the randomness of the rank. So what KVV showed was that this algorithm is actually 1 minus 1 over E comparative, which is roughly 0.632. And this ratio is the best you could hope for, no matter how smart your algorithm is. So in this sense, the classic online bipartite matching problem is settled almost 30 years ago. Now, of course, following that, there are many extensions, such as introducing weights to the vertices, having random arrival order of the online vertices, and so on and so forth. Those extensions I'm not going to get into today. What I want to get into today is a new kind of extension. So if you look at this model, it has to assume that one side of the vertices are given to the algorithm upfront. Okay? And if you think about real-life applications, that's not necessarily true for all the scenarios. Let me give you one concrete example. Imagine you're running a real estate agency for the rental market such that the tenants and landlords will come and go in an online fashion. Maybe the first tenant comes and says that, okay, I'm looking for an apartment which satisfy certain requirements, maybe in terms of location, the size, and so on and so forth. And also I need it in 2 weeks. Okay? Now, some point, some landlord comes and say that I have an apartment that has this and that feature, and I'm looking for these kind of tenants. Now, a pair of tenant and landlord can be matched together if they mutually satisfy each other's requirement. In this case, suppose this pair actually satisfy each other's requirement. But the agency may want to wait a little bit because it's not the deadline of either the tenant or the landlord yet. So I may want to gather more information before I'm making any decision. Okay? So maybe I wait a little bit, I see a few more tenant and landlord. At some point, the landlord says that, okay, this is I really need to get my apartment out, and it's now or never. Okay? So at this point, maybe the real estate agency will pick one of the tenants, let's take the second one, and match these two, and they both leave the market. And the process goes on. At some point, it might be one of the tenants' deadline saying that I really need an apartment next day, so you have to match me to one of the apartment now. So again, match it to one of the apartment, and they leave the market, and the process goes on. So you can see that this is clearly a bipartite matching problem, right? And clearly, it has an online flavor. But you cannot really assume that the tenants are given to you upfront or the landlords or the apartments are available to you upfront. Both sides of the graph will arrive online. So motivated by a scenario like this one and others, we try to come up with a mathematical model, a new online model that will allow both sides of the vertices to come online, but also has enough mathematical structure that allow us to do some interesting competitive analysis for the problem. Okay? So here's the fully online model that we come up with. So there's an underlying graph. The vertices come and go. There will be two kind of time steps. The first kind will be the arrival of some vertex v, at which point the edges between v and the previously arrived vertices will be revealed to the algorithm. So notice that at this point, there might be some incident edges to v that are still unseen to the algorithm because they connect v to some vertices that has not arrived yet. Okay? And the other kind of time step will be the deadline of some vertex, which is basically the last chance that you can match v to someone if it's not matched yet. It's possible that v get matched way before its deadline, but if it hasn't, then this is the last chance. After that, you cannot match v to any of the neighbors. And here it's crucial to make the assumption that all the neighbors of a vertex will arrive before its deadline. So it's a necessary assumption in the sense that otherwise it's not a fair comparison. There will be an edge that cannot be exploited by the algorithm because it's past the deadline, but somehow it's exploited by the OPT, then, well, what can you do, right? On the other hand, when you come to concrete scenario like the housing market scenario, then it's also a natural assumption because, well, if you want to match a tenant and a landlord, they better have an overlapping time window. If the landlord posts the apartment in January and the tenant come in March, even though they satisfy each other's requirement, probably not feasible to match them. Okay? Yes?
Just one clarification. So in your model, when a new node arrives, does it declare its deadline at that time step, or it can?
Okay, so in our model, we do not assume that. Okay, so basically you get to know it's the deadline when he announced it, but you have one last chance to make decision after he announced this is my deadline.
But do you compare against an opt, which assumes that this deadline was known before?
Oh, optimal is in hindsight.
Optimal.
So,
Yeah, this is.
Yeah. All I assume is that you get to see all the incident edges before your deadline. Otherwise, there's nothing you can do. Okay?
You mean to say that all the vertices, the edges are only to the vertices which are before the, right? Yeah.
Yeah, before V's deadline.
Yes.
Basically, you are saying that if they don't have an overlapping time window, then they don't have an edge, basically. That's what all I'm saying.
Yeah.
Yes?
Are you thinking about like strategic players who may lie about their deadline?
No, not in this model. Yeah, but I can see why that's it. Yeah.
So the classical ranking would be a special case for that, right? Because
Exactly. That I plan to get into a few slides later, but yes, the classic model is a special case of this because you can think of all the offline vertices come at the very beginning, but have deadlines at the very end, while the online vertices basically come at a certain time step and has deadline in the next time step. Yeah. So this is a generalization in that sense. Okay. Okay, so and since we make this somewhat idealized assumption that after the V announced this is the deadline, you have one last chance to match V to some neighbor, then it is without loss that we assume lazy algorithm that only make decision at the deadlines of the vertices because they try to wait and for more information before they make any decision, right? Okay, so after we get this model, right, we look at it and think, now we have a fully online model, then there's no good reason to restrict ourselves to bipartite graphs anymore. In the old model, you assume part of the vertices are given to the algorithm upfront, and that gives a natural bipartition of the vertices. But now all the vertices are essentially symmetric rows, right? So there's no reason in this model that we need to assume that the graph is bipartite. And indeed, there are applications where you need to consider general graph. For example, the ride-sharing platform, which essentially saying that, okay, the ride requests are submitted to the platform in an online fashion. Each request simply says that, okay, I need to get from some point A to some point B, specify the pickup location and the destination. And each request will be active in the system for, let's say, a few minutes. And our goal is to match pairs of requests that are compatible in the sense that their pickup locations and destinations are reasonably close, and they have an overlapping time window. And in that case, we can match them and serve them with the same taxi or self-employed driver in some cases. Now, you can see that we can model requests as vertices in a general graph, and the edges are trying to encode the compatibility. Yes?
So in the right side example, it's a bipartite, right? You have the drivers to the right.
I'm not trying to match ride requests with drivers. Here, I'm trying to say I match two ride requests and make a carpool, and then we're not handling the other aspect, which try to match the request to the driver. Okay, so if we are trying to make this carpool or car sharing, then basically the request can be modeled as vertices in the general graph, and then the edges encode the compatibility, and this is essentially a fully online matching problem with general graph. Okay.
But are you still looking?
Yeah. Go ahead.
I guess it isn't bipartite because now writers can be matched with anybody.
So
It's not by.
it's not necessarily bipartite, right? Because now there's an edge between a pair of vertices or a pair of requests, as long as the pickup locations are close to each other. Now, notice that here it's possible that request A is close to request B is close to request C, but this kind of distance add up, and at some point, the first request is not compatible with the last request. So you shouldn't imagine they are just cliques. So it's really maybe with some structure, but in general, general graphs. Okay. Okay. So to recap, this is the fully online model, and we called it the fully online matching. And in case the underlying graph is the bipartite graph, we call it the fully online bipartite matching. Fully simply to make a distinction with the old model, which essentially having one side of the vertices given upfront. Okay. Okay, so now we have a new model. So we should ask ourselves, what is the right algorithm for this new model, and what is the right comparative ratio? Now, as already pointed out, this is a generalization of the old model, right? So you shouldn't hope to beat 1 minus 1 over E. The 1 minus 1 over E hardness result will carry over to this generalization. And it's fairly easy to show that the greedy algorithm still gives you 1/2. Okay, so the right answer will lie somewhere in the middle. And what is the right answer? So we ask ourselves, can we beat 0.5? Now, if we want to beat 0.5, the natural starting point would be to think about ranking and see whether that works in the new model, right? So in this case, the ranking algorithm simply pick a random permutation over all the vertices. And then whenever you reach at the deadline of some vertex, you look at all the unmatched neighbor and pick the one with the smallest rank. Okay? Now, some clarification is needed here. Some of you may ask, since the vertices are not given to you upfront, how do you pick the random permutation to begin with, right? So it turns out there's an implementation of ranking that can be easily generalized to this fully online model, which is on the arrival of a vertex, you pick a number YV uniformly at random between 0 and 1, and call this the rank of the vertex. And then you basically just match to the neighbor with the smallest y, and that's equivalent to picking a random permutation over all the vertices. And also, notice here that smaller rank means higher priority. And because I received some complaint about why this is the case, but if you think about it, when we have integral ranks, right, rank 1 is better than rank 2, and now I'm basically normalizing it to between 0 and 1. So, and also this treatment is more consistent with the previous work, so this is what we are going to use. But of course, you can easily translated if you want to use one to be higher priority. Okay. Okay. So this is the ranking algorithm. The short answer is that ranking works in the sense of it beats 1/2. So for bipartite graph, we show that it's 0.554. For general graph, we show that it's 0.521 competitive. The exact numbers are not super important to memorize here, but just get the message that they are greater than 1/2, pretty far away from 1 minus 1 over e. And also the best ratio that we get for bipartite graph is much better than the ratio that we get for general graph. So in a way, bipartite graph are much easier, at least as far as our techniques go. Okay? Yes?
Tight, I guess you said that.
I'll get to that. Okay? So they are not tight, but there are some hardness results showing that you cannot improve too much. And there are some post-stock update that I'm going to mention at the end. Okay? So for the next 20 minutes also, I want to be able to convey the main ideas behind the analysis. And I'll go over the high-level plan of the analysis for ranking in the old model and talk about what are the extra technical difficulties that we need in this fully online model. So here's a one-page recap of the high-level plan of how to analyze ranking, KVV ranking in the old model. And this is actually an analysis. Okay, I'm not going to talk about the original analysis 30 years ago, but this one 5 years ago by Nikhil here and Kamal Jain and Bobby Kleinberg, which was a randomized primordial technique, but I'm going to present a digestive version which can be viewed as a gain sharing mechanism. So here's the plan. So whenever a pair of vertex U and V matches, the algorithm gets a gain of 1, right? So imagine I'm going to share this gain of 1 between the two endpoints. For now, let's think about just 50-50, although that's not the final plan, okay? Now, the eventual goal is to show that for every single edge, the expected gain of the two endpoints sum to at least 1 minus 1 over e, or whatever comparative ratio that you are planning to show. Now, suppose you can get the second bullet point, then summing the gains over all the edges in OPT will prove the ratio. To see that, this is a very simple example of the run of let's say, a greedy algorithm. And suppose we are using a 1/2, 1/2 splitting of the gain. Then at the end of the day, the performance of the algorithm will be equal to the sum of the gain of all the vertices. And you can do the accounting slightly differently. Instead of going over all the vertices, let's look at all the edges in OPT. And for each edge, look at the two endpoints. Since it's a matching, right? So I'm counting each vertex once. So, and finally, for each edge, since you're doing things greedily, you won't let both endpoints unmatched, right? So you get at least 1/2 when you sum the gain of the two endpoints, and that gives you 1/2, okay? Now, of course, the reason that we are not beating 1/2 now is because this splitting of 1/2, 1/2 is too naive, and in particular, it doesn't make use of any special property of ranking, so we cannot hope to get better than 1/2. The idea to beat 1/2 is to share the gain based on the rank of the offline vertex, okay? Before I get into how exactly I'm going to share the gain, just the high-level plan, high-level idea of sharing the gain based on the rank of offline vertex does not immediately carry over to the fully online model because right now we don't have offline vertices, right? Okay, so how do I extend this? It turns out this is not too difficult. I need to introduce a notion of active and passive vertices. So in the fully online model, since we assume lazy algorithm, whenever some pair of vertices U and V match, it must be the deadline of one of the two endpoints, one of the two vertices. Let's say it's U's deadline. In this case, I'm going to say that U is the active vertex and V is the passive vertex in the sense that, well, U is the guy that actively look around its unmatched neighbor and pick the one that has the smallest rank, while V is sitting back and wait for you to make that decision. Okay? So, example, the first pair that we include in the housing market example was because the landlord has reached the deadline, and so the first edge, the landlord will be the active vertex and tenant will be the passive one. The second edge was because this tenant reached the deadline, so the tenant will be the active one and the landlord will be the passive one. Okay? So as a simple fact, once we fix any edge, if this edge was ever chosen into the algorithm, then the active vertex is always the one with the earlier deadline because by design, that's the order that you make the matching decision. And the intuition here is that active vertex plays a similar role as the online vertex in the old model. in the sense that they are actively looking around the neighbor and pick the one with the smallest rank, while the passive vertex plays a similar role as the offline vertex. So with this intuition in mind, we're simply going to split the gain depending on the rank of the passive vertex whenever we consider the gain sharing of a particular edge. Okay, now we are ready to go through a warm-up case, think about bipartite graphs specifically. In this case, it's relatively straightforward. So as I mentioned, we're going to fix some non-decreasing function g to be chosen in the analysis. And then whenever u and v matches with u active and v passive, the passive vertex will get a share that depends on its own rank, in particular g of yv, and u is going to get the remaining. Okay? So the plan is to show that for every edge, the expected gain is going to be greater than 0.55. And just like the old analysis, we will look at this expectation in a very controlled way. We are going to fix the rank of all the vertices other than u and v, and only think about the expectation over the randomness of yu and yv. Okay? So what we need at this point is a good enough characterization of how the matching status of u and v changes as their rank changes. So all of these will look very familiar with, if you know the old analysis. I'll point out the differences. We need some monotonicity property. In particular, if the passive vertex, if vertex v in the final matching is active and unmatched, what does that mean? Is that it's unpopular in the sense that no one chooses to pick this vertex up to this vertex deadline. Okay? Then further increasing the rank of v will not change the matching because it will remain less and less popular and no one will pick it, and therefore doesn't change anything. So if v is already popular and is passively matched, then further decreasing the rank will make it even more popular, so it will remain passive. It's possible that it will get matched by some other vertices, but it will never change from passive to unmatched or active. Okay? So the proof is very essentially the same as the proof of monotonicity in the old model. If you don't know that proof, doesn't matter. Hopefully, it will at least make intuitive sense to you. Okay? So what this monotonicity implies is that there should exist a marginal rank, right? A marginal rank theta, such that whenever V's rank is smaller than theta, it's popular enough and is matched passively in the final outcome. Whenever its rank is above theta, then it's not popular and it has to wait until its deadline, so it's either unmatched or actively matched. So what the picture look like is that, okay, yv changes from 0 to 1. In the first segment, from 0 to theta, v is matched passively, in which case, I know pretty well how much gain v is going to get, right? By definition, it's going to get g of yv in this interval. If v's rank is larger than theta, it's not popular, so it's active or unmatched. Well, if it's active, I have some gain. If it's unmatched, I get 0, but since we're looking at worst case analysis, you might as well just assume that v is unmatched for the purpose of this talk, at least. So looking at this picture, we have a pretty good characterization of the expected gain of v when yv changes. In the first interval, g of yv. In the second interval, gets 0. Now, let's look at the gain of u as yv changes. So whenever yv is greater than theta, meaning that v is unmatched, then u has to get matched, right? It's a greedy procedure. So there are two possibilities. It matched passively or it matched actively. So if it matched passively, meaning that some other vertex, let's say w, choose u, by definition, it gets g of yu, depending on its own rank. If you match actively to some other vertex z, then just like the old days, you can argue that the rank of z is at least as good as the marginal rank of v. Otherwise, well, what is v doing, right? V just need to get marginally lower than yz in order to grab u's attention in that case, right? So theta should be at most as good as yz, and therefore yu is always, the gain of u is always lower bounded by 1 minus g theta. So in the old model, we will only have the right-hand side. There's no left-hand side here. But in the new model, u could be matched passively, and in which case we have the left-hand side case. So to sum up, we have the following bound for alpha u whenever yv is greater than the marginal rank theta. Okay? finally, we need to look at what happens to U when V is popular, when its rank is smaller than theta. Okay? So imagine what happens when YV go from slightly above theta to slightly below theta. It would trigger a alternating path, right? For those of you who are familiar with familiar with matching. So the alternating path start with some other vertex W, decide to choose V over its original neighbor because V becomes more popular. So, okay, and in this case, Z becomes available, which will further trigger some alternating path. I'm going to skip a little bit of detail here, but at a high level, what you want to show is that all the vertices on the right-hand side of this alternating path will get better. Okay, so in the old model, this is obvious because every time the right-hand side vertices change its matching decision, it's because it actively chooses a better neighbor, right? So it has to get better. But now the right-hand side vertices may change from active match to passive match. So we need to embed another notion of what does it mean to get better. So here we're saying it's better in the sense that assuming that they prefer to get matched earlier. So they always prefers to get matched passively before the deadline over match actively at the deadline. And if they're matching passively, they prefer to get matched even earlier. And if they have to match actively at the deadline, they prefer, of course, match to a better neighbor. Now, in this sense of better and worse, all the vertices on the right-hand side will get better. Okay? And at high level, because of that, you can argue that, okay, we will get essentially the same lower bound on the gain of alpha U, even though V's become popular and triggers a alternating path, because U, in the bipartite case, has to appear on the right-hand side. Okay? If it doesn't appear, then it doesn't change anything. So, of course, the same bound holds. If it appears on the right-hand side, by argument, it only gets better. Okay? Okay, so that basically wraps up the analysis for the bipartite case. If you look at this total gain, it looks very similar to the old result, except that in the second term, instead of having simply 1 minus g of theta, I now have the mean of 1 minus g of theta and g of yu. Okay? Now, we don't have too much of a control on what is the value of theta. It could be anywhere between 0 and 1, depending on the graph structure. So we're just going to look at the worst case and take the mean over all the theta. Now, notice that in this case, when we take the mean over theta, this number still depends on yu, the rank of u, right? So at the end of the day, we'll need to take this integration between 0 and 1, which is essentially taking the expectation over u's rank. And choosing this gain-sharing function, those of you who know the old proof will realize that this is actually the same gain-sharing function as in the old analysis. If a passive vertex has rank y, it will get a share that equals to e to the y minus 1. Now, I want to remark that even back then, we know that this is not the best gain-sharing function, even if we just stick with this analysis. But when we try to optimize it, the gain is just too small in the third digit after the decimal point, and the analysis just gets too messy, so we just stick with this clean gain-sharing function. Okay?
I see. So, but you know it's very close to optimal.
No. A better analysis will improve this ratio, as I'll mention towards the end. But if we stick with this analysis, stick with this lower bounds on the total gain, then even if you optimize G, you're not going to get too much better than this 0.554. The right answer for the performance of ranking in bipartite graphs is actually somewhat better.
Okay, so if you stick with this bound,
okay,
then this is close to the optimal function.
Yeah, no matter what G function that you choose, you're not going to get too much better than this.
Because it was the old model, this was the optimal.
Yeah, in the old model, this was the optimal because without the mean, then this basically make that a constant number, 1 minus 1 over e, no matter what theta is, right? So, but in this model, if we stick with this analysis, it's still close to the optimal choice of function, and it gives a clean analysis, so that's why we use it. Okay, so to wrap up, for bipartite graph, it's actually fairly similar to the old analysis. You kind of need this simple idea of introducing the notion of passive and active vertices and the intuition that passive vertices are similar to offline vertices in the old model. And And also in the analysis, you have this annoying mean of the two terms, but other than that, it's very similar. Okay. Okay, how about general graphs? General graphs are actually much, much harder than the bipartite case. For a very simple reason, the third bullet point, the gain when yv is smaller than theta, is gone. Okay, so let's recall why we can show that the gain for u is more or less lower bounded by the same number, no matter yv and is above theta or below theta. It's because of this alternating path argument that all the right-hand side vertices will get better. And then in the bipartite case, u only appears on the right-hand side, right? Now, what I didn't say, but holds, is that all the vertices on the left-hand side actually gets worse. In particular, the last vertex, if it's on the left-hand side, then it will change from matched to unmatched. And for general graph, you may very well be on the left-hand side. So in the worst-case scenario, it could be that you're getting 0 from this case. And once you have that, essentially you have to multiply the second term by 1 minus theta because you're only getting this gain in that interval. And suppose you have this worst bound that it doesn't matter how smart your g function is, you cannot beat 0.5. Which makes sense, right? Because the whole argument is saying that either v is matched or u is matched, right? And then with this simple argument, you cannot possibly hope to beat 0.5. Okay, so this is pretty bad, right? Because it's saying that the old gain sharing plan doesn't work no matter how smart your gain sharing function is. So you need some kind of upgrade to the gain sharing mechanism. Okay, so to see what that upgrade is and why it works, let's look at a typical hard instance. So I'm going to imagine that v is always unmatched when it's unpopular, when its rank is larger than theta, and v is passively matched by some vertex w when its rank is below theta. And for simplicity, let's assume that it's going to be matched by the same w no matter how popular it is. Okay? And moreover, whenever v gets matched, the alternating path is such that u appear on the left-hand side as the last vertex, and therefore change from matched to unmatched. Now, the first question would be, could that really happen? And here's the example that this actually happened. On the top, we have the matching result when v is unpopular, when its rank is 0.9. In this case, let's say w is matched to this guy with rank 0.4, and u is matched. Now, when v's rank get much lower, then w opt to choose v over its original neighbor, and which triggers the match of these white vertices. Which one being active is not super important, but the point is that u is now unmatched. Okay? And I would like to make an observation that w is really the cause of v's misery or the trouble of this pair uv, in the sense that if w was removed from the picture, then v is going to get matched even if its rank is horrible, it's 0.9. Why is that? Well, if w is removed from the picture, right? Now, what happened before use that line will be identical to this graph here with w matched to v. And then what happened is that the two white vertices will continue to match each other, and then at use that line, you will look around. I know that u has no other unmatched neighbor, otherwise it will not become unmatched here, right? So the only unmatched neighbor to u will be v, and then you will pick v up. And in that case, v will get matched if w is removed from the picture. Okay? So here we say that, okay, w is responsible for v's trouble because, well, first of all, w is an active vertex. When he looks around, v is available, but w doesn't doesn't pick v, okay? But that happens all the time in ranking, so that doesn't mean anything. But also, if w is removed from the graph, then v will be matched, but when w is in the graph, v somehow becomes unmatched. So w is responsible for v's misery. So we say that v is the victim of w, and w need to send a compensation to v in the charging mechanism. Okay? Now, of course, this is just a motivating story, but the actual intuition is different from this one. But let me be a bit formal. So for every active vertex w at the end of the matching process, I'm going to define a victim of this vertex w. If there exists an unmatched neighbor of it, that would become matched when w is removed. Okay? Now, when that happens, W is going to send a compensation that depends on the rank of the neighbor that it matched to. Okay, so if W is matched to some vertex X, I'm going to send a compensation that depends on the rank of X. Of course, I want to choose the function such that, first of all, whatever share that W is getting is enough to pay for this compensation. And also, for some technical reason, I need H itself to be non-decreasing, but once we divide it by Y, it's non-increasing. But that's for technical reason in the analysis. Okay? Now, instead of getting to the math, I want to just give you some intuition why it makes sense to have W send a compensation to V to solve the problem. So one of the first questions that you may ask is, why isn't W itself in trouble? Right? We are borrowing some of the gain from W to solve to compensate for this pair UV, which run into trouble of not getting anything better than 1/2. But if W is in trouble itself in the sense that there's some edge, let's say W and X, such that we also get no better than 1/2, and you're borrowing from W, then maybe we're not actually solving the problem, right? So in order to understand that, let's try to see what conditions U and V must satisfy for them to be in trouble, in the sense that we only write down that worst case bound for their total gain that only give 1/2. So it must be the case that U and V have no unmatched neighbor other than each other. Okay? So it's obvious because, well, first of all, they cannot have any unmatched neighbor on the alternating path because they are matched throughout, right? And if V has some unmatched neighbor outside this alternating path, then it shouldn't be unmatched here, right? And if U has some unmatched neighbor outside the alternating path, then on the right-hand side case, U shouldn't be the last vertex of the alternating path, and U cannot be that bad as unmatched. Okay? So U and V must have no unmatched neighbor other than each other, and also U and V never matches each other when V's rank changes. So both of these conditions must satisfy in order to get that worst case bound on their total gain. Okay? So what I'm going to show you is that for W, no matter which attribute that we're talking about, either one of these two assumptions must fail, and therefore W is, in a sense, in a better shape than U and V, and therefore it makes sense to borrow something from W. So now let's consider edge W and X. If X is V, which could be the case, right? V is a neighbor of W. Then I know for sure that, well, W sometimes matches X when V's rank is low enough. By our assumption, W is choosing V on top of its original neighbor, right? So in that sense, the second condition fail. If X is not V, then I know that W at least sometimes has an unmatched neighbor, namely V, other than X. And in that case, the first condition will fail for this edge. So to wrap up, no matter which edge or incident to W that we're looking into, W is never in deep trouble, or at least not in as much trouble as this pair UV, so it kind of makes sense to borrow something from W. Now, some other concerns, you might ask, okay, how many victims could an active vertex have? If I'm sending sort of compensation to multiple neighbors, then maybe I'm in trouble, or I don't have enough gain to share to them. Now, since we define the victim to be the vertex in the alternating path, that changed from matched to unmatched, right? So there could be at most one such vertex, because removing W will trigger only one alternating path. So you're sending compensation to at most one victim, but a poor vertex may be the victim of multiple W. That could happen, but any active vertex will send compensation to at most one victim. And also, after we introduce this new mechanic, does U and V need to send out compensation? Because if that's the case, then maybe we need to think about, okay, what's the balancing factor of these two parts, right? If I'm receiving some compensation, but I'm also sending something out, then it's not clear whether that's helping or not. In particular, U is the guy that is actively matched sometimes, right, by our assumption. But because U has no other unmatched neighbor, and the victim has to be an unmatched neighbor of it, right? So U is not sending out any compensation. Okay? So, I mean, the actual bound will look a bit uglier than okay, so this is the bound for the typical case that we assume. The first term is just like the old days, just from 0 to theta, I get the passive gain for V. The second one is the old gain for U, except that I need to multiply by 1 minus theta, because only in this interval I can truly have that bound. And finally, I have the extra gain from the compensation. Okay? The actual proof is more complicated because without the idealized assumption, it might be the case that, okay, U is sometimes actively matched to some other vertices and therefore need to send compensation. So in that case, you need to sort of think about the balancing terms a little bit. But I'm going to skip this part and just say that these are just technicalities that you can handle easily. Really, all you need to think about is that typical case and why the charging mechanism makes sense in that typical case. Okay, so you ask about negative results, okay? So here's the negative result that we can show. We show that even for bipartite graph, ranking is no better than 0.567. You may wonder what this number is. This is the omega constant, the solution to x times e to the x equals to 1. So a gap, but it at least shows that the best performance for ranking is fairly far from 1 minus 1 over e, even for bipartite graph. And also we show that no algorithm can be better than 0.63 something. The point is this number is strictly smaller than 1 minus 1 over e. So in this problem, you cannot hope to get all the way to 1 minus 1 over e, no matter how smart your algorithm is. Okay? Okay, so I want to also mention some post-doc updates. So the results that I mentioned so far are the results in the stock paper that published a couple of months ago. But we also get a little bit of improvement. In particular, we know that this omega constant is actually the right answer for ranking on bipartite graph. But the analysis need to get a bit more involved than the one that I just presented and deviate a bit further from the old model. And also, we look at another classic algorithm for the classic online bipartite matching problem known as water filling, and we show that the ratio for this algorithm is exactly 2 minus square root 2, 0.585. The interesting thing here is that the upper bound, or the positive result, holds for arbitrary graphs, while the lower bound only make use of bipartite graphs. So when fractional algorithm is of concern, or at least water filling algorithm is of concern, then bipartite graph and general graphs are equally hard in that sense. Okay?
So
yeah.
This is a fractional.
This is a fractional algorithm, of course, yes. And by the way, the lower bound holds for any algorithm that's oblivious to the edges between the remaining vertices, which I'll get to in the next slide, which is sort of one of the open directions that one can explore. Yes?
So for general graphs, you will lose an integrality gap of 2/3 if you are maintaining an integral matching, and it's a primal dual analysis. So is this one of the reasons why this fractional matching gives you better than ranking?
It could be, but even for bipartite graph, it gives better than ranking, right?
Yeah, that's correct.
So in a way, so this sort of says there's a separation between these two because there was, in the old model, this was a intuition that ranking can be viewed as a randomized rounding of water filling, but at least when you generalize to fully online model, that ceases to hold in the sense that there's a gap between their performance even for bipartite graphs. Yes.
One other follow-up question, just about this integrality gap. Is there any hope of, if you want integral matching in general graphs, so throwing in these more complicated blossom constraints and improving that competitive ratio?
It might be possible, but I really don't know the answer to that. So I have no idea how to make use of those constraints, basically. Yeah, that's one of the possible ways of improving that. But I think I'm going to mention it in the next slide. The more interesting direction for getting better ratio is to understand the role of these edges between the vertices that has arrived but not yet reached their deadline. Because so far we're talking about ranking algorithm and water filling algorithm that completely ignore those kind of information. And those kind of information are important, at least from the practical point of view, right? So it's interesting to look into that and see whether the theory research or worst case comparator ratio has something to say about how to make use of those information. Okay, so I'm going to wrap up with some open problems, although I already sort of hint on one of them. So one is that is general graph fundamentally harder than bipartite graphs? You can see that in the analysis of ranking, considering general graph does introduce a lot of trouble, and we get a worse ratio. But for the fractional problem and water level algorithm, well, it's not. Okay, so we really don't know whether bipartite graphs are fundamentally easier than general graph. And I also want to mention that among all the hardness result, like the hardness result for ranking, the hardness result for water filling, and the sort of the problem hardness that holds for arbitrary algorithm, we only make use of bipartite graph. We have no idea how to sort of exploit the fact that the graph is general to make the problem harder.
So can we just quickly summarize again about fractional algorithms?
Okay, yeah.
I'm a little confused.
Yeah.
So water filling gets this competitive ratio for general and bipartite.
Yes.
Okay. It's no better than this for
Any sort of algorithm that's oblivious to those remaining graph structure.
okay.
So a way to phrase what does it mean that the algorithm ignore the graph structure is that the graph algorithm that works in the stronger edge arrival model, where basically each time step is the arrival of an edge, and the deadline of a vertex is after the arrival of all its incident edges. That way you can sort of hide all the information in the remaining graph. And both ranking and water filling will work in that stronger model. And in that stronger model, it's not possible to beat this number.
Do these competitive ratio bonds also hold
in that stronger model? Because the algorithm doesn't make use of those kind of information. You might as well assume that those edges haven't arrived yet. Okay, so again, like first problem is general graphs fundamentally harder than bipartite graph. So far, we have no idea how to exploit the fact that it's general graph and make the instance harder.
Also for fractional, you showed an upper bound better than unmatched over E. Does it hold for fractional?
Yeah, fractional. Yeah. Hold for fractional as well. In general, I have no idea how to make use of integrality to make the problem harder either. So. Okay, so the other question, which I already hint on, is to beat 0.5, like 2 minus square root of 2. And the reason why this is interesting is because this lower bound holds for any algorithm that sort of ignore the edges between the remaining vertices that has arrived but not yet reached their deadline. Okay, and I think those structures are important, and in particular, we try very hard to show this is actually a hardness result for arbitrary algorithm, and the trouble that we run into is the structure of those remaining between those remaining vertices are always a tell of their identity, and you cannot really hide their identity in this model. So, but on the other hand, we don't have a concrete idea of how to exploit that as an algorithmic idea. And finally, it kind of makes sense to consider the weighted version, but we need to be a bit careful here. If we still allow the vertex arrival to be arbitrary, then there's not much that you can do. There's a very strong hardness result. And there are 2 independent papers by 2 groups, Ashlagi et al. And Dutta and Scholli. They sort of consider the weighted version with the 5-fold assumption in the sense that the earlier a vertex arrives, the earlier it's going to be out of the market or reach the deadline. Okay. Now, in that case, they can get some constant comparative ratio. The constant comparative ratio is like a quarter. And the hardness result stands at 1/2 for the weighted version in the 5-fold model. So there's still a pretty large gap. And also, I would say that the current algorithmic idea in these 2 papers are still a bit primitive. So it doesn't bring in any of these randomized primordial kind of charging argument into their analysis or algorithm. So there might be room for a lot of improvement in this end. Okay.
What's the difference between these 2 results?
They more or less get the same comparative ratio with similar ideas in the algorithm, but the actual analysis, the core math, of course, you can translate one to the other, but the presentation are different. So they more or less come up with the same result. You can say that.
It's the same model?
Same model.
I'm still sort of confused.
Yeah.
In even the original KVV setting,
Yeah.
if you handle weight, if you your line weights on the edges,
Yes.
then you need to have be able to revoke
Free disposal, right?
Free disposal.
But with the 5-fold assumption, you don't need that. If you think about
I
it,
didn't understand what that was.
okay, with the 5-fold assumption, so what's the hard instance that force you to make use of free disposal is that, okay, you give you an edge, a neighbor has some whatever weight, and once you choose to pick it, then you come up with an edge with a much larger weight. If you decide to pick it, you come up with an edge with even larger weight, right? But if you think about it in the 5-fold order, you can only do it once. Suppose the left-hand side vertex is U, and the first vertex V comes with weight 1, right? and you decide to pick it, and then the next vertex v prime comes. But what that means is that v prime must come after u, right? If v prime is come after u, then you cannot do it again because you must have to have another vertex v prime that's a neighbor of u that has to come before use that line, right? So and you can only force u to make the decision at its deadline. So basically, to do that trick, one of the vertices has to come before this vertex, and one of them has to come after this vertex arrival, and you can only do it once. And if you can only do it once, you can just randomize and guess 1/2 whether you should accept the first one. So it turns out that very strong hardness result goes away in the FIFO assumption. So and actually, let's say in the ride-sharing application, it kind of makes sense to assume FIFO. At least they approximately hold in terms of those requests. The requests that arrive earlier are quite likely to leave earlier, right? So it makes sense to assume FIFO in those applications. So I think it's a really interesting model to think about. Yes?
Ride-sharing applications, what if 3 people want to take the same ride? You get
I mean, you can talk about all those extensions as well, but I really don't know the answer. Right now, I'm just trying to come up with one clean model that I can do some analysis, but also capture some aspect of those scenarios.
Yeah, that's a good question.
Yeah.
If you had 3 uniform hypergraphs,
I don't know. I don't know the answer.
it gives you still 1/3.
Could be. I don't know the answer since I haven't really.
Fully on the hypermatch.
Might be interesting. I mean, yeah. So I think for this work, what we're trying to answer is like, is it possible to get interesting analysis in this fully online model? Now, once we know some basic ideas to do that, of course, we can look at all those extensions and see if the ideas carries over. Right now, I don't know the answer off the top of my head. Yeah. Okay, so that's it for the talk, and I'm happy to take more questions.